right, we are recording. We are now in section 9.7. Okay, so your first exam covers sections 9.1 through 9.7, those seven sections. This is the final section. And let's go ahead and look at it, look at a few examples. So what is this about? Cylindrical and spherical coordinates. What is this about? Well, how many of you remember in Calculus 2, you learned polar coordinates? You know, you're used to Cartesian coordinates, x, y coordinates, but then you also probably learned about polar coordinates, where you can plot a point in the xy plane using a radius and an angle. How many recall that experience? Okay, Alexander does, Logan does, wonderful. Wonderful. Simon, great, great. So the idea here is analogous for three-dimensional space. We have the x, y, z coordinate system, but sometimes other coordinate systems are more convenient, hence cylindrical and spherical coordinates. So we're going to do cylindrical coordinates first. And so just a little review, okay, based on figure 1 here. So this is, you know, the xy plane, and you have an angle theta measured from the positive x-axis and a radius r, and there is a polar coordinate and a Cartesian coordinate. And of course, above, let me just, hold on, I got a lot of windows open here. Let me click a few of them off. One moment. Right, so these are standard formulas that you have learned in Calculus 2 and your trigonometry class that you would have had. And we can utilize these to help us with cylindrical coordinates. So what is a cylindrical coordinate? What is a cylindrical coordinate? Well, in a cylindrical coordinate system, and I'd like to try to highlight this if I can. Okay, so in cylindrical coordinates, that's for 3 dimensions. You have, instead of an x, a y, and a z coordinate, you have coordinates, you have a radius coordinate r, you have a angle coordinate theta, and a z coordinate, which is just z. And the r and the theta stay exactly the same as you learned in polar coordinates. So in figure 2, they show you the cylindrical coordinates of a point. Okay, cylindrical coordinates of a point. And so you start at the origin, and you rotate an angle theta from the positive x-axis, and then you move forward a radius r in the xy plane, and then you move up or down a value of z. And that is a cylindrical coordinate. Now, cylindrical coordinates are, you're going to find they're sometimes more convenient to use than Cartesian coordinates. And of course, oftentimes what we want to do is convert cylindrical coordinates into Cartesian coordinates and vice versa. And so these formulas that you learned in trigonometry are very helpful. So let's take a look at an example here. One moment. Okay, I'm gonna go right in from the book on this one. So example 1. Okay, they say, okay, let me move this up a little bit. let's plot the point that has cylindrical coordinates given by radius of 2, theta of 2 pi over 3, and z equals 1, and then find the corresponding rectangular coordinates. So to plot the point, okay, not hard to do, not hard to do. Here in figure 3, they've plotted the point, and you can see, well, 2 pi over 3 is how many degrees? So that they're moving at an angle, but it's more than 90 degrees, right? Based on figure 3, 2 pi over 3 is more than 90 degrees. So if let's think about it. Let me go to the whiteboard real quick. Okay, so 2 pi over 3. Well, let's talk about that. That's in radians. All right, so let's convert it in degrees. That's right. So I appreciate all the answers. Arian, Logan, Marina, that's right. So how do you convert? Well, we put pi radians below, and how many degrees are in pi radians? You remember? I mean, you should know, but 180. Good. Good. 180 degrees. Good. IB, Alexander, and Norina. So, you know, the pi's simplify out, and we're left here with 2 times 180. Well, we can even do a little bit more than that, right? We can, 3 goes into 180 60 times. So this is going to give us 120 degrees, 120 degrees. Okay, just a little refresher there on how to convert from radians to degrees. It's very handy to convert from radians to degrees because, you know, it just helps when we picture things. So, okay, let's go back to the problem we were looking at. So now in the picture, we're rotating, we're going 120 degrees, moving out a radius of 2, and then moving up a distance of 1. And that is how you graph a polar coordinate. Now, what we want to do next is find out the Cartesian coordinate that goes with that. The Cartesian coordinate, we know that the x coordinate is going to have to be negative, the y coordinate is going to be positive, and the z coordinate is already 1. So let's go ahead here and go up a little bit. So now they are finding the Cartesian coordinates for that point. X is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. And of course, you know, I think you know the cosine of 120 degrees is -1/2 because the reference angle is 60 degrees. Okay, and cosine of 60 is 1/2. So, but you're in the second quadrant, so -1/2. And don't forget, I have the unit circle there in Blackboard under handouts. That unit circle is available. You can access it on the exam if you want. All right, and then y is, well, the sine of 2 pi over 3, sine of 120 degrees is √3/2. So you get √3. Okay, so hopefully you have these values, you know these values, you just know them, but you know, that's fine. So sure enough, the x coordinate's -1, the y coordinate's positive, and z is 1. So that's how you convert from cylindrical to rectangular. Now, in the next part of this problem, okay, now what we want to do is we want to find cylindrical coordinates of the point with rectangular coordinates 3, -3, and -7. Okay, 3, -3, -7. Okay, let me go to the whiteboard for a minute. Okay, so 3, -3, and -7. So we have, this is x, y, and z. So based on the fact that x is 3 and y is -3, okay, if we just think about the xy plane, 3, here's the origin, 3 and -3 is here. This is 3, this is -3. So if we, draw our little radius there and put in our theta, here's theta. Well, if we complete the right triangle here, what's this reference angle here equal to? How many degrees? Well, you're close, Alberto, you're close. I want to find this, what I mean is, okay, I'm focusing on this green angle here. I'd like to know what the reference angle is, like what that angle is. It's some angle between 0 and 90. Okay, good, 45 degrees. Good, good, good. So this is 45 degrees. Hold on now, hold on, I gotta turn this, my thing goes crazy hold on, I got something crazy going on here with my pen. Hold on, one moment. All right, one moment. Hang on here, one moment. We're really focused on the picture here, so this is just junk here, right? Sometimes there's no replacement for the mouse. Okay, so this is 45 degrees, and so theta has to indeed be 315 degrees. 315 degrees is what in terms of radians? Because WebAssign, you have to have your coordinates in terms of radians. What are we going to multiply 315 degrees by? Good, Lexi. Pi over 180 degrees. So let's see. 45 goes in 180 degrees 4 times, and it goes in 715 degrees 7 times. And so 7 pi over 4 is, yeah, I just have to let that pen alone for a minute. Hold on, I just have to do it this way. Let's talk about, so we want the cylindrical coordinates, right? Cylindrical is r theta and z. Well, theta is 7 pi over 4. And the radius here is in red. It's that red part there. So that would just be the radius would just be, by the Pythagorean theorem, the square root of 3 squared plus negative 3 squared, which is the square root of 18. But simplified radical form, that's equal to 3 times the square root of 2. So here we have 3 times the square root of 2 for the radius. And then z would just stay negative 7. And that's how you find the cylindrical coordinate for that rectangular coordinate. So that finishes up example 1. Are there any questions on that? All right, let's go back here then to the book. Here we go. So there's the answer. Okay, now sometimes, okay, like if you have a cylinder here with radius c has Cartesian equation x squared plus y squared equals c squared. But the cylindrical equation, the equation in cylindrical coordinates for this cylinder is just r equals c. Now, why is that? Well, let me show you. So let's just say you had, hold on, this is going to act right. All right, let's say you had x squared plus y squared equals 4. Okay, that's a cylinder. In calculus 3, that represents a cylinder with radius 2, right? That's a cylinder, a vertical cylinder. And I'm sorry, my picture's drawn kind of quickly. Vertical cylinder with radius 2. But x squared plus y squared, remember, equals r squared. So if r squared equals 4, r equals 2. So you have 2 ways to represent this surface. This is the Cartesian equation. Which you grew up with. And then you have a cylindrical equation. Okay, 2 ways, and because cylinders work great with cylindrical coordinates, you can see the second equation is easier than the first equation. It's just the cylinders more easily described in terms of cylindrical coordinates. So, we can take surfaces like, for instance, like example 2. Oh, let me make it visible here. Hold on. Example 2 says, describe the surface whose equation in cylindrical coordinates is z equals r. Okay, well, what you can do is you can say, okay, they're showing it here. Hold on. If z equals r, then z squared equals r squared. But r squared is x squared plus y squared. But z squared equals x squared plus y squared, it turns out, is the equation of a cone. And you can see that that's where a and b and c would equal 1. It's like your standard cone, but that's an equation of a cone. So you see a cone has a very simple equation in cylindrical coordinates. Are there any questions so far? Give me a thumbs up if you're good so far. Excellent. Yeva, Alexander, Mary, Marina, Angela, and hold on here. Alberto, good. Oh, wait, hold on. Down here. Yep, Alberto, Logan, Brian, wonderful. Simon, good, good. Okay, okay. And Arian, of course. All right, wonderful. This is basically, we've talked about cylindrical coordinates. Now we have to talk about spherical coordinates. Spherical coordinates. So spherical coordinates, okay. Okay, I'm going to try to highlight as much of this as I can. Maybe that's fine. One moment, class. Okay, so spherical coordinates, you have what's called a Greek symbol rho, which is a radius, but it's a different radius than the polar coordinate radius. You have an angle theta. Now, theta is the same as what you know theta to be. And then you have this third angle called phi. Okay, so let's see here. Let me just. Okay, so spherical coordinate. Okay, so rho, theta, and phi. So I'll just, this is rho, theta you know, and this is phi. So how would a spherical coordinate work? Well, let's go ahead and take a look. By the way, with spherical coordinates, rho, well, no, let me get to the picture here. Let me get to the picture next. Here in figure 6 are the spherical coordinates of a point. So generally, I find it easiest to, since theta I'm familiar with, I measure theta, if I'm given a spherical coordinate, I measure theta from the positive x-axis, and then there is an angle phi that's measured from the positive z-axis downward. Okay, so theta, you you think of like holding a line segment, rotating it some angle theta in the xy plane, and then positioning it so it's phi radians down from the positive z-axis. And then you move out a radius r, and that's called a spherical coordinate. That's called a spherical coordinate. Now, it turns out that we have some nice conversion formulas also for spherical coordinates. And again, you're going to have the ebook available on the exam, so you can access these formulas. But, all right, so x is rho sine of phi cosine theta, y is rho sine of phi sine theta, and z equals rho cosine phi. Those are the conversion formulas that take you from spherical coordinates to rectangular coordinates. Now, the way they can be derived is they talk about it here in figure 10. Okay, in figure 10 here. Well, they have a picture that helps you to that might help you to understand. So, like, take hold on here. X equals rho sine phi cosine theta. So if you look in the xy plane, the cosine of theta is equal to x over r. Okay, x over r. Okay, so let me just tell you what, let me kind of do it step by step here. You ought to at least see why one of these conversion formulas works. If I can show you one, you can figure out the other. Okay, so this again, this is, you know, section 9.6, figure 10. So based on the picture, cosine of theta is x over r, which means x is equal to r cosine theta. Now, we're happy with cosine theta, but the radius r, okay, I mean the spherical coordinate is given by rho, theta, and phi. So I'd like to find out what the radius r is in terms of these spherical coordinates. So for that, we go back to the picture. Okay, back to figure 10. And there is a vertical triangle. There's a vertical triangle, a right triangle, that has that radius r in it, and it has an angle phi. Okay. Now, if you were to, let me just see here. Notice the angle phi in the triangle at the top. It's that way because of the phi measured from the positive z-axis is equivalent to the phi in the vertical triangle because of alternate interior angles. So what we have to do is we have to show that that x is equal to rho sine of phi. That's what we have to do. I'm sorry, I'm not saying, we have to show that r, the radius r, okay, in the bottom triangle is equal to rho times the sine of phi. Well, if you look at the phi at the top, if you take the sine of phi, sine is opposite over hypotenuse, right? So the sine of phi is the radius r divided by, that's the opposite side, over the hypotenuse rho. You see that in that vertical triangle? If you look at the phi at top there, at the top, the vertical red triangle in figure 10, the sine of phi, opposite the sine of phi is that radius r. And then in that right triangle, for that vertical right triangle, the rho is the hypotenuse. So this means then, if we go back to the whiteboard, this means that, well, I mean, we have then that the sine of phi is equal to r over rho. And so r, well, rho times the sine of phi is equal to that radius r. And so you see, we can replace now this r here with rho times the sine of phi. And so therefore x is equal to rho times the sine of phi times the cosine of theta. Okay, and this justifies the first, those three conversion formulas. It justifies the x. The other two you can get just by looking at figure 10. So now we have this and those three conversion formulas, and we also notice that rho squared is equal to x squared plus y squared plus z squared. Okay, rho squared is equal to x squared plus y squared plus z squared. Now, we can show that. That's probably worth showing. It only takes a minute. So, let's see here. Okay, if you take x squared plus y squared plus z squared, remember x is rho sine of phi cosine theta, we square that. Y is rho sine of phi sine of theta, we square that. And z is rho cosine phi, we square that. So what we're going to get is rho squared sine squared phi cosine squared theta plus rho squared times sine squared phi sine squared theta plus rho squared cosine squared phi, right? All right, now let me just check one thing here. Okay. So what we can do here is we can factor out a rho squared from everywhere. So we have rho squared times sine squared phi cosine squared theta plus sine squared phi sine squared theta. Hold on, I don't want that yet. Plus cosine squared phi. But if we look here, we can factor out a sine squared phi, right? So we'd have sine squared phi times cosine squared theta plus sine squared theta. But what's cosine squared theta plus sine squared theta equal to? Do you remember the trig identity? Very good, Lexi. It equals 1. And so now what you're left with now is you're left with, I mean, if I just kind of continue it up here, what you're left with is rho squared. So now I'm taking all of this I'm putting it here. You're left with rho squared times sine squared phi plus cosine squared phi, right? But that just equals rho squared times 1. I mean, it's an angle, right? Phi is an angle. And so x squared plus y squared plus z squared equals rho squared. All right, and we showed that. Pretty cool, huh? Pretty cool. Okay, so let's go back to the thing here, back to the book. So in the book, they say, okay, example 4. This point is given in spherical coordinates. Plot the point and find its rectangular coordinates. So the point is 2, well, it has a rho of 2, a theta of pi over 4, and a phi of pi over 3. Okay, so what would the point look like? Well, let's see. Figure 11. There it is. So phi is 45 degrees. Pi over 3 is 60 degrees, and then you move out. So phi is measured from the positive z-axis. And by the way, phi is always between 0 and 180 degrees. Theta can go from 0 to 360 degrees, but phi is always from 0 to 180 degrees. Basically, you're measuring, if you were to measure from the positive z-axis, if you were to measure from, if you were, okay, hold on. So if this, wait, wrong thing. Here's the origin, z-axis. So if you were to measure from here to here, what's phi equal to for that angle? How many degrees? 90. Good. which is pi over 2. Good, Lexi. Now, if you were to measure from positive z-axis to here, what would phi be equal to? How many degrees? 180. Good, Brian. Good. So 180 degrees is pi. So you see, but you don't need phi to range any further. I mean, again, phi is between pi and 0. Theta standard goes between 0 and 360 degrees. But the idea, as you see, is if phi stays between 0 and pi, but you want to get a point over here, all you have to do is just pick an angle theta that gets you over in those octants over there, you see. So you don't need phi to go from 0 to 2 pi. You need theta to go from 0 to 360 degrees. But phi, you can let it go from 0 to 180 degrees. And in fact, it's restricted from 0 to 180 degrees. Because if you don't restrict it, then you're going to have multiple. You'll be able to represent a spherical coordinate using like an infinite number. Well, like more than one. A point in space could be represented by multiple equivalent spherical coordinates, and we want to try to keep things unique for our purposes. So, okay, let's go back to the ebook here. Are there any questions so far? Pretty cool stuff. All right, well, now, if we want to convert from rectangular to spherical coordinates, okay, find the spherical coordinates for the point. So this point, 0, with Cartesian coordinates or rectangular coordinates, 0, 2 root 3, negative 2, the rho is going to equal 4. You see how they're doing the rho? And based on the y and the z, I want to be a little careful here. Just give me a moment here. So let me go to the whiteboard. I'm trying to do things that will, help you. Well, I'm trying to be helpful. But for this problem, this is example 5 from section 9.7. They tell you, okay, this is a rectangular coordinate, x, y, and z, okay? If we focus on just the YZ part, okay? So, y is positive 2 root 3 and z is negative 2. We're down here. Okay, there's the point. So I'm just dealing, with y and z. So y is 2 root 3 and z is negative 2. But the phi, angle phi, so, I'll just kind of draw a little thing here. Okay, so phi is measured from the positive z-axis. And based on the right triangle here, what would this reference angle be here? Is it 45 degrees, 30 degrees, or 60 degrees? Because you know we're always doing reference angles in trigonometry. What's that reference angle going to equal? I'll call it alpha. What's that reference angle going to be? How many degrees? Based on the fact that this is, well, hold that thought, Brian. This is 2 root 3. That side's 2 root 3. This side's -2. I probably didn't draw it exactly to scale, but it's not. Yeah, so I think, yeah, that's right. It's going to be. I'll tell you what. Let me do maybe a little. Let me do a little bit better with it. Okay. Hold on. Maybe I can. One moment. Okay, so 2 root 3, have it go a little longer, and -2 like that. Okay, so I'm just making the picture a little better. I think Brian got maybe a little confused because it looked like a 45-degree angle, right? But this is a little more, you know, it's just a little more accurate. Okay, this picture. So here's the point right here. With coordinates 2 root 3, -2. Now, what's that phi going to equal? What's this reference angle going to be? You can see it's not going to be 45 degrees. So is it 30 degrees or 60 degrees? Yeah, hold that thought. There's something I'm doing wrong here. That's 30, but there's something I don't like here. No, I like it. I like it. It's good. Yep. That's 30 degrees. Yep, I'm liking it. So then what's the green? Good, everybody. Good. Brian and everybody. So what's this phi? What's, I'm sorry, I don't mean to have phi here. I don't mean to have phi here. I mean, I mean phi, but I'm not writing phi. I'm writing, that's phi, right? That's the angle phi. That's what I'm not writing. I'm writing theta where I want phi. You understand? Phi is measured. Heck, I'm just going to put it in black. There. So this phi here, yeah, 120 degrees. Good, Logan. Or 2 pi over 3. Okay? So, you know, the in terms of the let me just see here. Okay, and let's go back to the thing here, the problem. One moment. So they found phi this way. I did it sort of geometrically with you. But for this problem, they found phi by, since z is rho cosine phi is z over rho. They put in z equals -2, rho equals 4, cosine of phi is -1/2, so phi is 2 pi over 3. That's another way to get it. And the cosine of theta is, well, remember, x is rho times the, x is rho times the sine of phi cosine theta. So cosine of theta is x over rho times the sine of phi. Well, that equals 0. That equals 0 because x was equal to 0. And so theta is 90 degrees. The cosine of 90 degrees equals 0. Okay, so this then justifies then their answer for this problem. Okay. Now I'll mention this. I'll just mention this in passing. It says a little warning here, because I know some of you are going to be taking physics or there's not universal agreement on notation for spherical coordinates. Most books on physics reverse the meanings of phi, of theta and phi, and use r in place of rho. I don't know if you've seen that. You've probably not seen this yet. But you know, don't worry about it because we're going to use our notation. Okay, but that's just a little thing to mention. Okay, so I think let's see here. I think we're pretty good. Let me just take a peek at something real quick. Okay, one moment. Let me just. I'm just peeking at the homework here. I'm going to activate that homework for 9-7. I want you to work a little on that. And let's see. Just looking at it, making sure that basically what we covered, you know, you ought to be okay. Now, occasionally, by the way, an angle theta, like for this homework in set number 6, the angle theta is not going to be a nice angle. Okay, it's not going to be a nice angle. So it's going to be a decimal. So you're going to put in a decimal. So the way WebAssign wants it, because I have a tight numerical tolerance on the answers, because sometimes a student will do a problem wrong and get an answer, and just by luck, it turns out that it's equal to the answer. So, but that happens very seldom. But in the 5th question in the homework, the angle theta is not going to be a nice angle like pi over 6 or pi over 4 or 2 pi over 3 or you know 5 pi over 3. You know, so you got to put in a decimal like 6.23, something like that. Okay, for number 6. I'm just mentioning that. But the rest of the problems I think look pretty good. The last 2 are multiple choice, so be a little careful with those. And I think that's basically good. So, are there any questions here before I stop the recording? I want to give you some time to work on this section 9.7. Who's feeling good? Give me a thumbs up if at least so far you're good. Wonderful, wonderful. All right. Well, let's see if you can get this you know, a good part of this assignment done. And I'm actually, excellent, Brandon. I'm actually going to stay an extra half hour tonight till 10 o'clock, just in case you want to work, you know, on this section 9.7 more while I'm here, in case you have questions. because I have to put this on your exam, because if I don't, then the second exam is going to have like a lot of sections, and it's going to make it harder. So this section's not hard. I think you can manage it on for this next exam. So let me stop the recording. Your first exam. All right.